Good morning, ECNC class. Um, it's Monday morning, about 10:30 a.m., and this is going to be at least part of the lecture for tomorrow, and I'll get this link out to you shortly. So this is where we left off in the compressed air slides. We're looking at compressed air distribution systems. So let's take a look here. We just have some pictures of receiver tanks, different compressed air. There's one coming in on a flatbed trailer. There's vertical tanks. Most of them are vertical. Occasionally you see a horizontal one. This is actually a desk and dryer. That's a heatless. That's a 15% purge unit. There's a storage tank there. Probably a compressor sitting over here. At any rate, let's go on here. Okay, so we're going to talk about storage, compressed air storage. All compressor systems need storage to smooth out pressure fluctuation caused by intermittent demands or users. So, a lot of compressed air users open up and blow a significant amount of compressed air for maybe a few seconds or 10 seconds, 15 seconds. And so it's enough to really affect the pressure, especially locally, unless there's air stored, like a big tank that's at fairly high pressure, then it takes longer for the system pressure to blow down for a given use. So it really smooths out the pressure fluctuation. Lubricant injected rotary screw compressor systems need minimum of 3 and 5 to 10 gallons per CFM of trim compressor capacity. So the trim compressor is the one that's reacting to changes in plant demand. In a well-controlled system, we would like to have just one trim compressor. And it's nice if it's a VFD machine. So you might be running 10 other compressors, but you got one big VFD that handles the load swings and reacts efficiently and quickly to maintain a fairly stable system pressure. And by having more storage in the system, you can smooth it out even more. The old rule of thumb is more storage is better, and it's a one-time cost. You got to pay for it once, but I mean, the tank ought to be good for a long time, especially if you keep the moisture out of it from internal corrosion. Consider secondary or dedicated storage for high volume, short duration applications. We'll see that. We talk about primary storage, which is up around that kind of assists the compressors. And then out in the system, secondary storage, where you might put around one large compressed air user, and when it opens up, pull the air out of a storage tank instead of sucking down pressure in the system is kind of the idea of it. Okay, rules of thumb for sizing storage. Well, in the old days, they used to say, use the system piping as storage, which is true. I mean, all the volume of piping, that stores air as well. Bigger systems, larger diameter of pipes, it can be a fair amount of storage in the piping system. Receivers not required. That was in the old days with reciprocating type compressors. Probably not so good. Inlet modulation, that control scheme, doesn't benefit as much. It's just terrible all the time unless the compressor runs pretty much fully loaded. But its energy use is not affected as much, even though system pressure fluctuations would be by having a small amount of storage. So 1 gallon per CFM, that's in the old days of the big double acting recip compressors, running a 10 pound band between load and unload control. They could get by pretty well on 1 gallon per CFM on that trim machine. But since we don't see many of those, most things have gone either to centrifugal for the big systems or rotary screw, primarily lube injected rotary screw, which the 3 to 10 gallons per CFM applies to. So improves part load efficiency of load unload lubricant injected air compressors. So this goes back to the old plot of current. This is the 100 horsepower Carlisle air compressor. And you can see it's cycling up and down pretty quick, and the current never really falls. When the plant's under production, we get a lunch break or an extended period, and the demand falls, and you see the compressor can unload and go down about 47, 48 amps, whereas before it's barely cracking 60 amps. So if you could add enough storage, you can make all those short cycles look more like the long cycle, and you can reduce the energy used by the compressor. And that has to do with blowing down that sump. It takes about 40 seconds to get the pressure off, and that's going to put us down in this region. And then if we could stay unloaded for a couple of minutes, we could sit down here and not use hardly any, relatively speaking. So this is the unload amps on the compressor. This is the full load amps up here as the pressure rises. And we recall this is our banana curve, which shows that if we have 10 gallons per CFM on this puppy, then we get pretty much a flat curve, which as we run at lower percent capacities, the power falls pretty good at 40%. We're 60% on the compressor, whereas if we only have 1 gallon per CFM, we're clear up here about 81, 82% of full load input power. And that's a bunch of energy if it happens for a long time during the year. So we could go from the top curve to the bottom curve by adding storage. Okay, so here's a little equation we can use for air receiver sizing. And we'll talk about primary and secondary, but we can use the same equations. V is the volume of the tank that we need, and this comes out in cubic feet. And so then usually buy them in gallons, so you have to multiply by about 7.5, it's 7.4805 gallons per cubic foot. So time is a time interval in minutes. C is the air requirement, the total air requirement, and cap is the capacity of the compressor. So let's say the whole system needs 2,000 CFM and we're running 1,500 of capacity, then C minus C cap is 500, and we're wanting to supply that for a short-term spike out of a primary storage system. So the bracket term is the airflow that we want to come out of the storage tank. PA is just the absolute atmospheric pressure, PSIA, 14.5, 14.7, you know, it could be less if you're in Denver. And P1 minus P2, this is the allowable pressure drop basically for the system or for that tank. So let's say we're going to have the system sitting at 110 and we have this big event that increases the air demand 500 above the compressor, but it only lasts for 20 seconds. And the allowable pressure drop is 110 down to 90. So that would be a 20 PSI drop. And so then this will tell us the volume of the tank needed to supply that flow rate for that period of time. So it takes a little thinking about it. And we can, depending on what we know, we can rearrange this. We could solve for a volume. If we know a volume and we know the rest of this, we could solve for the amount of time that it will take for that tank to go from the high pressure to the low pressure, etc. Okay. So we have supply side, which is called primary storage. And then we have demand side, which is out by a big compressed air user, which we talk about as secondary storage. So primary storage improves compressor control response. It smooths things out. You don't have the thing slamming load, unload every 5 or 10 seconds, which is not good efficiency and it's not good for the machine. So it's just additional pneumatic energy is stored in that tank. And the other thing that's pretty good, if you have an unanticipated compressor shutdown, it gives you time. You know, you can size it to give you between 1.5, 2 minutes for somebody to run and start another compressor if you don't have automatic startup on your system. And that can actually be quite important. You know, if compressed air is critical to your operation, you probably would want to have automatic startup on your backup compressor. But if you don't, when that storage will give you some time for somebody to go sprinting through the plant and start the backup compressor. On the secondary storage, high volume, intermediate demand, dedicated storage, improve speed and thrust, increase system volume, stabilize pressure, all that sort of thing. Okay, so here's a little example. So calculate the required primary storage volume. So we need 226 CFM airflow from storage for 1.5 minutes. We've got 100 psig compressor load pressure, and the minimum system pressure we want to tolerate is 90, so we can have a 10-pound drop. So how much volume of storage do we need to put in to supply that 226 CFM for 1.5 minutes? Well, you just apply that previous equation. And so you see volume is time in minutes times the flow rate that you want out of the tank times the atmospheric pressure in absolute times the delta P. So plugging in those numbers, we get 491 cubic feet, which times 7.48 is 3,673 gallons. So you'd probably, round up from there. You'd probably wind up with 37 or 3,800 gallons in this. And so the recommendation here is to put roughly what, 2/3 of it in, I'm sorry, 3/4 of it roughly, you can calculate the percent, 3,000 gallons into a dry receiver and about 660 or more, 700, whatever number you like. I cut and pasted this from some example, and that's what they put in there. So I suspect that plant had a 660 gallon receiver, and they added the 3,000, and they stuck the small one as wet receiver. But you typically will have more dry air stored, but a little bit of wet air storage helps that dryer drop some moisture out. And you see the zero loss drain traps down here on the bottom by everything. That's pretty good. Okay. So we can also talk about dedicated storage. And so this then shows our compressor room set up, and then we feed out through our distribution system. And so say we have a critical machine over here that's not shown that we have to supply air to, but it's just an intermittent use, but it's important. And so what we do is we put in this tank that's sized to provide the airflow that it needs from whatever the supply line pressure is down to the minimum pressure that's okay for the machine. And we charge it slower. We put a check valve in so that the air can flow from the distribution line into and charge this tank. But let's say that the tank was charged and everything was good, and something happened down here and the air pressure went down in the distribution line. Well, if you don't have a check valve, you can bleed air backwards, and you can partially uncharge your tank, drop pressure in it back into the distribution system. And you don't want to do that because this is a critical machine. So you put in a check valve where it can charge this way, but it can't come back out. And you usually put an orifice in here so that you, after this thing blows down and empties the tank, you slowly refill this tank, just as long as you have plenty of time to get the pressure back up before this critical machine goes through another cycle and needs more air. So an orifice and a check valve are typically installed on the supply line to the dedicated storage tank. Okay, and then the supply line comes on out. And what we're showing here is a lot of times we want to slant these lines down so that any condensate will flow into a point like a storage tank where we have a drain trap and we can get it out of the system. Well, if you got a long plant and you pitch this a little bit, after a while, that compressed air line is getting pretty low in the ceiling, and you can't just let it get too low. So what you can do is you can stop the line, you can put in secondary, or this is shown as general system volume. And so you run that into the tank, and then you can, if this is a tall tank, you can raise that line back up and get it up close to the ceiling. Gives you an opportunity to do that. And it doesn't matter really how tall the tank is, just as long as you don't you don't fill it up with water, which you shouldn't if the trap works right. And then you can run this pipe up high again and then let it come down again. Okay. And so now we're showing another receiver, and this is a high volume intermittent demand. And so we've gone through the equation to solve this receiver size. And so this shows the refill valve, and there would be a check valve, and would limit the rate at which this thing can receive air. Once it comes up to pressure, it's ready. This thing, maybe you're blowing down a big filter or something, so it takes a couple minutes and the air comes out of this tank. So it doesn't affect the general distribution system. And then the tank slowly fills in anticipation of the next cycle. So that's kind of primary and secondary storage. Okay, so I've got a little example here. We've got a scenario with a system operates two 200 horsepower lube injected rotary screw compressors. Compressed air use is typically steady at 800 CFM, except for one filter blowdown. So once per hour, there is a 15-second air use at 600 CFM, and that's on top of the 800. And so that's going to put us at what, 1400 CFM. So, you know, in a 200 horsepower compressor, one 200 horsepower is going to be someplace, you know, over, well, if it's 450, it's going to be 900. So probably between 900 and 1000 CFM. So you can operate one compressor until, except for this 15 seconds. So every time that thing blows down at 1400 CFM, you're going to have to auto start that second compressor. Well, that's kind of a pain in the rear, and it's not very efficient. And so let's see if we can't size a receiver tank to take care of that. So the plant wants to size the storage tank to supply the 600 CFM use and operate just one compressor. System pressure is maintained at 100 psig nominally and can briefly drop to 85 without causing a problem. So we can let it go down for a short period and everything's okay. We don't want to go below 85. Okay. So we're going to take ambient pressure at sea level, 14.7. So 15 seconds divided by 60 is 0.25 minutes. And so 0.25 minutes, this is the capacity of the compressor. The one compressor is 950. Our compressed air demand during that blowdown event is 1400. So that's what we want to come out of the tank. What is that? 450 CFM for 15 seconds. And we can have a 15 PSI drop. So we get about 110 cubic feet, which is about 825 gallons. So if I was doing this, I'd probably put in 1,000-gallon tank just to have a little extra. Like, you know, maybe they can find one, maybe a sister plant. If it's a big company, they may have a sister plant that has one they don't need. Okay, so here's some more on sizing secondary storage. Here's an example where we have compressor capacity of 350 CFM, actual CFM, discharge pressure of 100 psig, steady process demand of 300, so it fits. We've got 50 extra. Intermittent demand, so we've got another 100 CFM for 10 minutes per hour. So our peak demand then is our 300 steady plus the 100 is 400. And this just calculates the average demand in the system, which we really don't need, but we did it anyway. And so then we just, you know, it's the same. It's about like that previous example. So we're going to plug in 10 for the minutes. We're going to plug in 350 minus 300 or 50 is what's going to have to come out of the tank because we're 300 actual and we got an extra 50 CFM in compressor capacity. So we need 50 out of here, PA, and the delta P. We can go down in this case, I think we can go down 10 PSI. So plugging in those numbers, we get 735 cubic feet. And there you go. Or you can turn it around. If you knew the receiver volume, you want to know how long it would take for it to drop 10 PSI, then it would come out 10 minutes. Just rearrange it. Okay, there's more of the same, just showing the being able to rearrange the equation based on whatever you know, uh, and whatever you might want to solve for. Okay, so let's look at minimize system pressure drop. Pressure drop through the compressed air lines is always an important consideration. So some general notes. We want to design for the lowest possible pressure drop, delta P. Main distribution piping should shoot for 1% to 2% of the total. So if you got 100 PSI out of the compressor, your main piping should be 1 to 2 PSI drop. A branch main, maybe 2 to 3% drop. We want to pitch the pipes. This is for condensate to drain back through a drain trap, 1 inch per 100 feet. So, you know, if you had a 1,000-foot plant, that's 10 inches. 2,000-foot plant, that's 20 inches. So that's, it starts, if it goes long enough, it starts getting down pretty close to the floor. Dryers, size appropriately, pay attention to the pressure drop on dryers and filters. Size them for pressure drop, not pipe size. Gauges, we want to put pressure gauges across all of the components. With quick disconnects are good, so you can change out your pressure gauges easily, because we really want to monitor the pressure drop across all those components. Leaks, we have planned and unplanned, like a time drain trap is a planned leak. Some uses, you're blowing down a filter, that's basically a planned leak. So we may have to increase demand, therefore pressure drop. So if we have more leaks, then we'll have a bigger drop in pressure. We'll have to up the amount of air that we generate. Consider low pressure drop disconnects. You can buy, a lot of pneumatic tools are on the end of these curly rubber hoses, and you can buy those things in smaller diameter. You can get them up to 5/8 of an inch at least, which, is bigger than a half. And so you know how much pressure drop. You put a small hose on that thing, you may have 100 pounds in the supply line, but you may have 65 at the device, because that curly cord or hose can be 15, 20 feet long. And so that can be a huge pressure drop, which can cause you to increase compressor pressure, which costs you money. So that's something to think about on the disconnects and hoses that feed particular users. Here we go. Here is loss of air pressure at 100 psi G pressure due to friction in psi per 1,000 foot of pipe length. So this is the rating on the compressor. The ratings on the compressor are at that inlet air, or they're calling it equivalent delivery in cubic foot of free air. So that's the air going into the compressor. So, if we had let's say we had a 200 horsepower compressor, it might be rated for 1,000 CFM. So free air, that's the 1,000. When you compress it in the pipe to 100, it shrinks down. It's about a factor of 8 to 126.5 is the actual volume flow rate inside the pipe, but that's not how the compressor is rated. Okay, but say we had that. So we're going to put in this 1,000 CFM compressor. We have to size the compressed air lines that are going to distribute that air. Well, if we put in a 2-inch line, every 1,000 feet is going to have almost a 77 PSI drop. That's probably not acceptable. If we put in 2.5-inch line, it's going to have almost a 30 PSI drop. That's not acceptable. A 3-inch line is 9.3. That's still too much. 3.5, that's just a weird pipe size. So you're probably going to put a 4-inch line on that thing, which would tell you that every 1,000 foot of pipe is going to drop 2.21 PSI. Or you could even go 5-inch, in which case you would have not much of a drop at all. Okay, so let's see here. That's what's going on this one. So you can use this to get an idea based on your flow, what size pipe you should have present. This is another chart that does kind of the same thing. We've got pressure drop and where'd I go? Shouldn't use the mouse. My pressure drop per sound. I don't know. I don't want to put this one in there. I don't even like it. Okay, so pressure loss through screwed pipe fittings. You can find charts like this. So let's say we had a 4-inch component actual inside. Let's say it's a gate valve. And so it's that valve in the wide open position is equivalent to 2.35 feet of straight pipe. So for every gate valve, you can add up the actual length and then add an equivalent length for all of the different types of fittings. You can have a long radius elbow at 4 inches. A long radius is 4 feet. A standard elbow is almost 8 feet of additional length. An angled valve, and you can find all kinds of information on this. That's just a little bit, but it's out there to let you calculate the overall equivalent length of your piping system, including the fittings. Okay, air velocity in the pipe. Let's remember recommended air velocity inside compressed air piping is between 20 and 30 feet per second. A common design value is 20 feet per second. The actual CFM inside the pipe, compressed, is divided by, so the actual CFM, I'm sorry, the free air into the compressor is divided by the compression ratio using absolute pressures to determine the volume flow rate at pressure inside the pipe. So if we had that 1,000 CFM air compressor, 200 horse rated at 1,000, then inside the pipe, we would take, as I say, if it's rated at 100 psig, that's 114, say 0.7 psia, and divided by 114.70, I think it's like 7.81 or something. And so then you would divide the 1,000 by the 7.81 to get the volume flow rate at pressure inside the pipe. And then divide that by the cross-sectional area of the pipe, and it'll give you the feet per second flow rate. The volume flow rate at pressure is then divided by the cross-sectional area of the pipe to determine the average flow velocity inside the pipe. So here's an example. So there's 1,000 ACFM flowing in a 3-inch diameter pipe at 100 psig with a standard pressure, we're saying atmospheric pressure of 14.5 psig. So here's the pipe cross-sectional area, just pi d squared over 4. So 3-inch divided by 12 to get feet, squared by 4.0491 square feet. Compression ratio. So we're 100 plus 14.7. And so what we're saying here is that the 14.5 is the pressure at which the air actually gets into the compressor. We've got a little drop across the inlet filter, so we're taking into account that. 14.7 is the ambient, and so the 14.7 divided by 14.5 is 7.91 is the compression ratio. So then I take the volume flow. The volume flow at pressure is that nominal flow at inlet conditions divided by the 7.91, or it's about 126.42 CFM inside the pipe at 100 psig. And so the velocity in the pipe is the 126.42 divided by the cross-sectional area, 0.0491. And then we're in minutes here, and I want to go to seconds. So I throw the 60 in to convert the minutes to seconds, and I get 42.9, which is too fast. What I recommended is 20 to 30. And so, a design value is about 20. And so it's too high. And so we're going to have a large pressure drop per 1,000 foot of pipe. So when I look on the table, I get 9.3 psi per 1,000 foot, which is too much. And that shows it coming out of the table. So there's the 126 and a half. There's the 1,000. These are the two CFMs, basically at inlet and at pressure. And so I would probably want a 4-inch pipe for this. Okay. System pressure profile. So this is, let's say, if we had load and unload compressors, they might be bouncing back and forth between, you know, a load pressure of 100 and an unload pressure of 110. So we get fluctuation. But we've got some pressure drop across dryers and filters. Hopefully it's not huge. This shows a pretty big one. And then we have distribution system piping, and then filter, regulator, lubricators, valves, hoses, disconnect, all this stuff before we get to the end user. So if you're doing an evaluation of a system, it's good to draw a diagram like this to kind of show you how the pressure drops occur through the system. You can do it in a design, then you can go out and look at gauges and see what you're really getting in person to see if what's happening in the field is appropriate based on the design. Maintenance, proper maintenance can help minimize pressure drops. You got to change all these air oil separators, you know, change them before they reach their maximum pressure drops. We usually pay off. Filters, all that stuff get dirty, have to be changed, inlet or intake filters. So we got to do our maintenance. This slide is talking about where to measure pressures in the system, and basically, you know, so the compressors would have a pressure gauge on their discharge pressure. We show a wet receiver tank, so we'd have pressure here, so we could see any pressure drop between these components. And then from here across the filter, we can measure pressure across the dryer, across this receiver, and then out to here and in use. So we want to be able to measure pressure drop across all these different components. Compressed air leaks. And let's see where we are in this. Yeah, we better keep mushing on here. Okay, so leaks are obviously a source of financial loss. Leaks in a typical air system can be as much as 20 to 40% of the total air production. Typical is probably 20 to 30%. Reduce the amount of air leaks to less than 10% would be considered world-class on a big system. It's hard to do. It takes a concentrated, consistent effort. Leaks can be planned or unplanned. A planned leak would be, it could be a vortex cabinet cooler. You can blow compressed air across a little vortex device and it gets quite cold, and you put those in electrical cabinets to keep the cabinet from getting too warm in the summertime. But they just blow compressed air all the time. There's other ways to do that. Air can be used for parts ejection. It's a planned leak. You've got a press stamping out parts, bam, and the air blows it out, bam, and the air blows it out. A leaking fitting or a cracked hose is obviously an unplanned leak. Use good quality hoses and disconnects, replace cracked filter bowls, develop a good leak remediation plan, and bring in experts. TVA will do free leak surveys. They won't fix them, but they'll find them and tag them for a company. They'll do typically one a year for them if they're requested. A good way to get something done for nothing for you. This just shows, we had this diagram before, and I mean, honestly, you can have leaks all over the place. And, you know, if they go unfixed, they can cost you a lot of money over the course of time. Discharge through an orifice. This is sometimes how we estimate the capacity blowing. I mean, people go in a laboratory and there's some equations you can use. And so, but people have measured this stuff. You know, you take a orifice plate and drill a 64th of an inch hole, put different pressures behind it and measure the flow rate. And so we see if we had a 1/4 inch, 60, almost 62 CFM at 70, goes up to over 90 CFM at 110. And remember, a typical compressed air might be 20 kW per 100. So, you know, if you're in this range, you're probably using 18 kW of compressor power to generate the air that you're leaking through that 1/4 inch leak. So, you know, you figure 18 kW over the course of a year, 18 kW times 8760 times whatever your average electrical cost is, it turns out to be a bunch of money. And you can go ahead and, calculate a cost of compressed air and then recast that table instead of in flow rates in terms of dollars per year. And so this is at 9 cent electricity and $0.25 or 25 cents per 1,000 cubic feet of the air cost. And so you see that what that quarter inch leak, that's, $11,000-$12,000 a year if you don't fix it. And you can have a bunch of these things. So it's a good idea to stay up with it. Okay, continuous system observation and identification of failures. Annual focused compressed air leak survey at least once a year. I want to go through the entire plant, tag leaks and fix them. Big plant, a lot of compressed air, maybe every 6 months. Keep a master database. You want to prioritize big leaks first, of course. Traps and drains are primary targets, and leak detection equipment can aid in doing this. Compressed air leaks can produce significant waste in a system, not only in terms of energy loss, but in terms of maintenance and equipment life. Leaks are a significant factor in determining long-range strategy. 1/8 of an inch diameter leak will discharge 15 CFM at 70, and that can cost over $2,000 a year. So we want to fix them. Reduce leak rate could possibly shut down one compressor. This is kind of the holy grail of leak reduction. If you can fix enough leaks that you can run one less compressor, that's usually a significant reduction in operating cost. The difference between the overall cost of generating compressed air and dollars per, say, 1,000 cubic feet and actual savings. So just because the energy saved at the compressor, so if you reduce the amount of air the compressor makes, that's good. But if you have an inefficient control system on the compressor, you may not save as much as you think you're going to. So the fixing the leaks is good, but we have to efficiently turn down the compressors in order to really save the money. Some things to keep in mind. Sometimes portions of plants shut down, that equipment gets abandoned, no longer used, and nobody remembered to disconnect the airline to this thing, and over time gaskets fail, and this thing could be sitting outside where nobody goes, just blowing compressed air continuously. So disconnect valve off compressed air supply if you have unused equipment. Leak problem areas, I mean, they can be all over the place. Couplings, hoses, tubes, fittings, flanges, disconnects, filters, regulators, lubricators known as FRLs, open condensate trap, pipe joints, I mean, all this stuff. Have some rules of thumb, get over that. Okay, so if we're running load, unload, I think we saw this before. You can estimate the percent on that particular compressor by, you can log that data. And so where T is, you pick a load cycle or you pick an average load cycle, it stays loaded for T, capital T. And then the total load cycle from load point to load point. So it loads and then it comes down, it's unloaded, and then it loads again. So you take the loaded time divided by the total cycle time times 100, and that's the percent. So you can either average or find a typical load cycle. Okay, compressed air use. I tell you what, I think I'm going to stop this one for now, and I'll post more later. We may have 2 or 3 more lectures to get through these slides, but I'll be back soon. I'll get this one posted and get the link out. You guys have a great day.